Okay, again, let me make sure I'm recording. Yes. All right. Let's go. Your information one, glomerular filtration. We talk about the renal membrane or filtration membrane in the renal corpuscle between the blood and the capsular space. We have a fenestrated endothelium. So here's the thing. Remember the permeability of capillaries. There's three types of permeabilities. There's the continuous capillaries that have endothelial cells with slits between them. Then you have fenestrated capillaries. That is capillaries with holes right through the cells, these endothelial cells, plus the slits between them. And that's called fenestrated. Fenestrate is Latin for window. And then there's the sinusoids, which have big, huge spaces between the endothelia, and like whole cells can leak out. Those only found in liver and in spleen. So you have the holes in the endothelial cells. You have some basement membrane between the endothelial cells and the filtration and the filtration slits on the podocytes. So you have the capillary membrane, some basement membrane, and then you have the podocytes right here, and they have these filtration slits. They're called podocytes because podo means foot, like toes or like fingers. They're like this, and they have slits between them. Then we're going to have to talk a little bit about capillary hydrodynamics. I know you don't want to talk about that, but we're going to about that first in the blood vessel chapter. We're talking about hydrostatic pressure and osmotic pressure. Right? And then we talked about that in the respiratory chapter also, where we learned that it's a really low pressure system. So the capillaries really favor reabsorption and very little secretion because in the capillaries of the lungs, osmotic pressure is always greater than hydrostatic. Well, now we have the exact opposite situation. In the kidneys, hydrostatic pressure is always greater than osmotic, and the pressure in these glomerular capillaries is high. It's higher than just about any of the capillaries in the body. So it's mostly secretion, not too much reabsorption. All right? So the blood hydrostatic pressure is a force pushing fluid out of the capillaries. The colloid osmotic pressure and the capsular hydrostatic pressure is both inhibiting that, is pushing in the other direction from the capsular space back into the blood. So you have to subtract those two forces from the blood hydrostatic pressure to get what's called a net filtration pressure, and that is out of the capillaries and into the capsular space. So here's a blow-up of to the left of the glomerular capillaries with the filtration membranes, the holes in the cells, and the podocytes, are also called a visceral layer of glomerular capsule, and called podocytes. And you can see they have little fingers or toes, if you want to call them, like this, and there's these slits between them. There are also mesangial cells, intraglomerular mesangial cells. For some reason, they show them in the diagram that can actually make these slits wider or make the slits smaller to increase or decrease the amount of fluid being filtered. All right. And the amount of fluid being filtered is glomerular filtration rate. How many milliliters per minute are being filtered? Okay. Then on the right, is a cross-section of the filtration membrane. To the left is blood, and to the right is capsular space. And so and it's important for you to know what's being filtered and what isn't being filtered. And it's fairly easy. Everything is filtered, except for formed elements and large proteins. Those are the only things that are not filtered. And you can see that to the left, you have leukocytes, erythrocytes, platelets, large proteins. They're not going anywhere. Filtrate includes water, glucose, amino acids, ions, urea, many hormones, vitamins B and C, ketones, and very small amounts of protein. Really small proteins can fit through the fenestrations of the capillaries and between the slits in the podocytes. Okay. So here is the situation with the hydrostatic and osmotic pressures. Don't worry about the numbers. I'm not going to give you problems, giving these numbers and you figure out net filtration rate. But the important thing is to look at what the net filtration direction is. So you can see hydrostatic pressure 60 out, 60 millimeters of mercury out. The osmotic pressures 32 in. Now, again, why is the osmotic pressure pushing fluid back into the capillaries? Because remember, the filtrate is close to a protein-free solution. And so there's more things dissolved in blood than there are in the filtrate. So the filtrate is more watery fluid than blood. So water wants to flow back into the blood. And then capsular hydrostatic pressure is all this fluid coming out of the blood into this very small space. It causes pressure to build up. And this pressure wants to push fluid back into the blood. But if you add up the osmotic pressure and capsular hydrostatic pressure and subtract it from blood hydrostatic pressure, you get a force, a net filtration pressure out. So the net force is pushing fluid out of the capillaries into the capillary space and then into the proximal convoluted tubule. So, glomerular filtration rate, milliliters per minute that are filtered by these nephrons, directly related to net filtration pressure. The greater the net filtration pressure, the greater the GFR. Increases fluid in solutes, decreasing absorption. That means an increase in fluid in solutes will mean there's more glomerular filtration, and it'll decrease the reabsorption. Okay. What you need to know is regulation of glomerular filtration. This has to be regulated so that it's constant over any changes in blood pressure. Your blood pressure can go up a little bit, down a little bit, but you want to keep glomerular filtration rate the same. This is part of homeostasis. Right? And there's various ways you can do that. Well, there's three ways you can do that, and this is typical for most stuff. There's autoregulation, happens right in the nephron itself, and then there's or intrinsic control, and then there's neural mechanisms to affect it, and there's hormonal mechanisms to affect it. So first look at autoregulation, intrinsic control. First is myogenic mechanism. And that is a fact that when you stretch smooth muscle, it reflexively contracts. When you relax smooth muscle, it reflexively contracts. So it wants to stay the same diameter. So that's called the myogenic mechanism. So if you get an increase in blood pressure and it dilates the arterio, the afferent arteriole constricts. I should say, but if the blood pressure goes down and the afferent arteriole gets a little smaller, then these muscle cells relax. They don't contract as before; they relax to try to stay the same opening over various blood pressures. But that's doesn't always work. What you need on top of that, as part of autoregulation, is what's called tubular glomerular feedback, and this involves the juxtaglomerular apparatus. The macula densa, the juxtaglomerular cells, they call the marginal cells, also in the mesangial cells. So I'm going to talk about how this thing works, how it senses something, which is going to be sodium concentration of the fluid in the distal convoluted tubule, and how it's going to cause a change in size of the afferent arteriole. And right now I'm going to tell you that really a regulation of GFR is all dependent upon the diameter of the afferent arteriole. They all affect that diameter. If you make the diameter larger, GFR goes up. More blood goes into the glomerulus, GFR goes up. The smaller you make the afferent arteriole, the less fluid goes into the glomerulus. The smaller GFR is. Okay, so at the bottom, here's what you want to do. Normal urine production maintained by renal autoregulation. So normal mean arterial pressure goes from, but pressure can go all the way from 80 to 180. And over all these different blood pressures, you want to maintain GFR constant over all these. No matter how blood pressure changes, you want to maintain GFR. So decrease in systemic blood pressure on the left widens arterioles, allows more blood in the glomerulus to offset a decrease in systemic blood pressure. Normal systemic blood pressure, we have a normal size of the arteriole. Increase in systemic blood pressure narrows arteriole lumen. It stretches the luminal arteriole, so reflexively constricts to keep GFR down, because if you had a really great amount of blood pressure, that would cause GFR to shoot up. So this is so it's autoregulation helps maintain GFR constant over different blood vessels, too low blood pressure or too high blood pressure. And then remember, it doesn't talk about how the juxtaglomerular apparatus works. Wait a minute. Okay, I got to talk about how juxtaglomerular apparatus works here. All right, let's go back. Okay, the juxtaglomerular apparatus. It's kind of a mysterious thing, in the sense that the macula densa cells detect the salt concentration of the filtrate in the distal convoluted tube. And here's the thing, we're going to get into what's happening in different parts of the nephron. And in the proximal convoluted tubule, its major function is to reabsorb lots of the stuff that was filtered at the glomerulus. Some of it 100%, like all the small proteins, like all of the glucose, lots of the sodium, potassium, calcium, all kinds of stuff, vitamins, everything is brought in. So a lot, like 60%, I think, of the filtrate at the glomerulus is reabsorbed in the proximal convoluted tube. And this is automatic. So it's like we don't have any control over these transport mechanisms, the glucose transport mechanisms, and say sodium ion transport mechanisms. They're automated. All right. So you can think of like I always use the analogy of a conveyor belt. You have this conveyor belt going by, and it goes by at a certain speed, and you'll have these automatic machines that take things off the conveyor belt at a particular rate, and they never change. They always go at the same rate. Right. So how much stuff is brought in, it depends upon how fast the conveyor belt is moving. If it moves too slowly, you will take out too much stuff. So think of it this way, you want to take out a certain amount of stuff, X amount of stuff you want to pull out. So if it goes real slow, then you'll end up taking out too much stuff. Right? And this stuff will be the low concentration down the line. And so the macrodenser cells can detect this, saying, wait a second, there's too little sodium in this fluid. Therefore, the GFR is too slow. We have to raise GFR. So what they'll do is tell the mesangial cells not to make this vasoconstrictor. And this vasoconstrictor is like unknown. They don't even know what it is. They just know it exists. And it will cause the afferent arteriole to relax, GFR will go up, and that'll cause the conveyor belt to go faster. If the conveyor belt goes too fast, then you don't take out enough. And the amount of this stuff is too much down the line. So the macrodenser cells realize, wait a second, there's not enough taken out. We need to take out, it goes too fast, so we have to slow down conveyor filtration rate because too much of it has been taken out. So the macrodenser cells will tell the mesangial cells, we got to slow down GFR, secrete this vasoconstrictor. Vasoconstrictor will cause constriction of the afferent arteriole, and this will slow down GFR, slow down conveyor belt, and we will have auto-regulated GFR. Okay. Let's get into then now neural regulation of glomerular filtration rate. Sympathetic innervation. And what that will cause is a constriction of the afferent arteriole. So that's what I'm saying. The regulation of GFR comes down to regulating the size of the afferent arteriole. So a lot of sympathetic stimulation will shut down your immune system. And that makes sense, right? It's a fight or flight system. So if you're in an emergency situation and you got to do something, you don't want to have to stop to pee in the meantime. You want to put that off to another time. Okay. Then there's hormonal stimulation, atrial natriuretic peptide and angiotensin II. Atrial natriuretic peptide will increase the size of the afferent arteriole, raise GFR. It'll do something else down the line in the nephron also, but it'll affect that at the vascular pole of the renal corpuscle. And then angiotensin II raises blood pressure, and this will cause and it causes vasoconstriction all over the body, including the afferent arteriole. So this will decrease GFR, and this will help increase blood pressure. All right. So let's get on to information 2, tubular reabsorption and secretion, and first look at the proximal convoluted tubule. Oh, first, before we do that, we look at decreasing GFR through sympathetic stimulation on the left, increasing GFR through atrial natriuretic peptide on the right. So stimulation, some kind of stress emergency, sympathetic stimulation of kidneys causes vasoconstriction of both the afferent and efferent arterioles. And actually, constricting efferent arterioles will actually raise GFR, but constricting afferent arterioles will decrease GFR. But the effective changing the shape of the afferent arteriole is much greater than the effect of constricting the efferent arteriole. So GFR is turned down. Granular cells of JG release renin. And remember, this causes the production of angiotensin II, which will cause contraction of the mesangial cells, the intraglomerular mesangial cells, and cause those filtration slits to become small. So less is filtrated, GFR goes down. Decrease in GFR, decrease in urine formation, retain fluid, maintain fluid volume. Opposite, increasing GFR through atrial natriuretic peptide. Increase of blood volume or blood pressure, atrial wall stretches, atrial natriuretic peptide is released by heart, causes vasodilation of afferent arteria. Result, increased blood flow into the glomerulus, increased GFR. Second, relaxation of mesangial cells. That does the exact opposite of sympathetic stimulation, causes the intraglomerular mesangial cells to relax. So slots become larger, more fluid is filtered, GFR goes up. Increase in GFR, increase in urine formation, loss of additional fluid, decrease in blood volume. All right. So reabsorption and secretion in tubules. Substances reabsorbed completely. And one of those is glucose. Glucose is 100% absorbed in the proximal convolute tubule. So by the time the filtrate gets to the loop of Haley, there is no glucose. In a normal person, I'm talking about diabetics, a normal person. And also, these small proteins are actually chewed up by enzymes, I think by membrane enzymes in the proximal convolute tubules. They're brought in as amino acids, and they're completely reabsorbed. So there's no small proteins or amino acids in the filtrate when it reaches the loop of Henle. So they're not regulated. So your kidneys don't regulate the amount of glucose in your blood or the amount of amino acids because they are 100% reabsorbed. What the kidney does regulate is things that it partially reabsorbs or partially secretes. So there ends up being a variable amount of these things in the kidney. That means the kidney regulates them. There is no glucose, there is no amino acid or protein in urine, therefore the kidneys don't regulate those. Regulated reabsorption will be things like ions, calcium ions, potassium ions, sodium ions, bicarbonate ions, hydrogen ions, all regulated, right? And they're all found normally in urine, either in a large amount or a small amount, depending upon whether you have too much or too little of them in your body. Right? Substances eliminated as waste products, such as urea. Urea is filtered at the glomerulus. It's both reabsorbed and secreted. It's strange that you reabsorb this waste product, but we do. The blood leaving the kidneys still has urea in it. It doesn't clear your body completely of urea. I think it takes out about 40% or something. And then also uric acid and creatinine. These are eliminated as waste products. Most reabsorption happens in PCT, as I mentioned. Large amount of things filtered at the glomerulus are reabsorbed in the PCT. I think like 60% of the things filtered at the glomerulus are reabsorbed in the PCT and reabsorbed automatically. That's reabsorption, but it's not regulated reabsorption. It's just automatic reabsorption. Oh, 65%. I said 65% glomerular filtration. Routes of reabsorption, transcellular and paracellular. Transcellular between the cell, paracellular within the cell, across the cells that line the tubule, and paracellular between the cells. Transport maximum renal threshold. Transport maximum is the maximum amount transported. So, as I said, in these automated systems in a proximal convoluted tubule, they have a transport maximum. They can only bring back a maximum amount of substance, like glucose. It's and that's where renal threshold comes in. The concentration of glucose in your blood is below the renal threshold and below the T sub M for the kidneys. So they can reabsorb 100% of the glucose that's filtered. But in an untreated diabetic, this glucose concentration gets so high, it gets above the renal threshold, above the T sub M. And now there's so much glucose that these automated systems cannot recover it all. And it ends up spilling into the rest of the nephron. And there aren't any more glucose transport proteins in the rest of the nephron, in the loop of Henle, in the distal convoluted tubule, or the collecting duct. So if the glucose makes it past the PCT, it ends up in the urine. So there's more what I've talked about. Substances reabsorb completely. Glucose by secondary active transport with sodium ions at the luminal membrane, which is the membrane that's facing the inside of the tubule, and by facilitated diffusion at the basolateral membrane, which is the bottom part of the tubular cell, which faces the interstitial fluid and the peritubular capillaries. And small proteins. Also, it's penocytosis across the luminal membrane. And then inside the cell, the small membranes are digested amino acid, transported across basolateral membrane by facilitated diffusion into the interstitial fluid, into the peritubular capillaries, and brought out with the blood that leaves the heart in the renal vein, leaves the kidneys in the renal vein. So here is a diagram showing the tubular fluid, high sodium, low glucose. These are brought in together. If you remember, that's called secondary active transport. It's also called synport. It uses the concentration, that sodium concentration gradient across the cell to bring glucose in. And then glucose is transported across the basolateral membrane by facilitated diffusion. And there are sodium-potassium pumps in the basolateral membrane to pump sodium out and pump potassium in to maintain that sodium concentration gradient so we can continue to do that. So 100% of glucose reabsorbed into the blood. So substances with regulated reabsorption. As I mentioned, what is regulation versus conservation? Conservation is bringing everything in, and it's not in the urine. So anything that's filtered and not in the urine in any way is conserved. So glucose and amino acids, small proteins. If you'll find this stuff in the urine in variable amounts from day to day, this is something that's regulated by the kidney. So sodium chloride. Sodium is regulated by the kidney, the sodium concentration in the blood. Reabsorbed along the entire nephron, facilitate diffusion at luminal membrane, active transport at basolateral. It comes across by secondary active transport, and it's active transport at the basolateral. Yeah, I should say that secondary active transport at luminal, active transport at basolateral. Regulated at DCT and collecting duct. So during the PCT, the sodium is reabsorbed mechanically, automatically, and not really regulated. It is regulated at the distal convoluted tubule and collecting duct under the influence of aldosterone and atrial natriuretic peptide. Aldosterone binds to principal cells, increases sodium resorption. So if aldosterone is present, more sodium is reabsorbed, and more liquid is reabsorbed, follows the sodium. AMP, exact opposite, antagonizes aldosterone, inhibits sodium reabsorption in both the PCT and collecting duct. So it's an antagonist of aldosterone. This is, by the way, aldosterone causes sodium reabsorption, but it causes potassium secretion. If you absorb a lot of sodium, you lose a lot of potassium. You don't absorb a lot of sodium, you save a lot of potassium. And there is the situation lumen of the proximal convoluted tubule, high sodium coming in. It's just facilitated diffusion. And then actively transported at the basolateral out, and then it enters the blood. And that is automatic. That's not regulation. The regulated part is on the right. We have principal cells, and you have aldosterone present. Wait a minute. We have sodium channels, and they come in, and depending upon how much aldosterone there is, will determine how much sodium comes in and how much is used. More aldosterone, more sodium coming in. Less aldosterone, less sodium. More aldosterone, more potassium losing. Less aldosterone, more potassium gaining. So sodium and potassium go in opposite directions under the influence of aldosterone. Okay, water reabsorption by osmosis through aquaporins or between cells. Aquaporins are proteins in the membrane that allow water to cross the membrane. Because water is a hydrophilic molecule, can't get across the membrane all by itself. So we, over the course of a day, we filter 180 liters of water, or about 1.5 liters is reabsorbed. So you should make out 1 to 2 liters of urine every day. It's obligatory in PCT. Another way of saying it's automatic, obligatory. It's not regulated, it comes in automatically. Water, because it follows the sodium that's being reabsorbed in PCT. Regulated in DCT and collecting ducts with aldosterone and ADH. Aldosterone, water, sodium and water coming, ADH, just water. It's facultative, which means it pulls in a lot of water if ADH is present. It doesn't pull in water, and you lose water in urine if it's not present. And so there's the ADH, the principal cell. ADH causes the principal cells to put in more aquaporins, more water comes in. And this is one of the major mechanisms to conserve water. Remember, diuresis is the making of large amount of dilute urine, so antidiuretic hormone prevents that. And you end up excreting very salty urine if you're dehydrated. Okay, let me talk about urine osmolarity on the next. So this was urinary 2. I'm going to call it right now, and then we'll see you later on the next video, urinary 3. All right, see you later.